Okay, so the third problem, we're given F net and M. And let me see how I phrased it. And I'm not sure I specified x not equals 0. And we're given x of t. Picture would be just one dimension. Okay, we start here. We'll go ahead and say we'll start at x naught equals 0. And we go through some given displacement. Okay? What can we do? Well, we know how far we go, we know where we start, and we know that wave motion equation x of t equals x naught plus v naught x plus vx, because we don't have okay, I'm going to write the v naught x t plus a at 1/2 ax t squared. Well, ax equals f net over m, because we're just Newton's second law. Okay? So we have an expression for this acceleration. And we're starting from rest in the first question. So v naught is 0. Okay, so we can get t. Now there's a symbol we can use, it's very simple. If you're given your x of t, well, never mind, we're going to do this, okay. So here's your t. Now we want to get the velocity. Okay, so here's where we just do the derivative. Simple derivative. We get this. We don't pull it out of a hat. We're secure in this if we understand the calculus of derivation. And we can take the derivative and get this because it's a very simple step. And we don't have to rely on our memory. Well, it's still good to remember this. You want to check it out by at least doing that derivative in your head. Make sure you got it right. Because it's not going to be generous with partial credit if you write that equation down wrong. Okay? Well, so you get 0 plus axt, which is just axt, but ax is f net over m. and T is 2m x of T over F net. So it turns out it doesn't matter what F net is. Something's not terribly wrong here. What did I do wrong? Oh, wait, T is the square root of all this, sorry. So, okay. We got a little bit of a mess, but that's what we have. So that the expression well, you square this, you're going to get a 2f net x of t in the numerator, and you're going to get an m in the denominator, so your m divides out. The 1/2 divides the 2, and yet you do a simple algebra, you get f net x of t. Very simple expression. If you keep your wits about you and do this for the second situation, okay, well this is initially v is 0, so 1/2 m v squared goes from 0 to f net x of t. Again, remember, the condition that you're working with was that v naught is 0, right? So the change in this quantity is equal to the net force times how far you move. Okay? Now, the second problem says, okay, well, let's assume that v naught x is not 0. Then, you're going to need a v naught x times t here. That's going to change some of these expressions, but I'll tell you in advance, if you do it right, what you end up with is the change in the 1/2 mv squared starts at 1/2 mv naught squared, right? It ends at something else, and if you subtract the 2, you still get this. And this is called the work that's done by the net force. So that gets us into work energy, which is chapter 6. And you don't have an assignment in chapter 6 until next week, but you want to start thinking about it. One thing we're going to do in Lab Friday, we're going to do some measurements that fit right into this. And some fairly sophisticated analysis. So what did you think through this? I recommend you kind of play around with the symbols and see what you get here. We'll make more sense of it next week. Okay, very good.